I'm going to walk you through the lab materials from Lab 7, moving the camera. So first thing you need to do is download and build the project files for this lab, which I have done. Okay, and if we just run run the program, you can see we're presented with our multiple cubes from Lab 6. And if you recall, in Lab 6 we created a camera class, which I'll show you here. Okay, so we created a camera class which calculated the view and projection matrices from a fixed position. So if I go to main.cpp, we can see we create a camera object, and our initial camera is located at coordinate 005. So what we're going to do in this lab is use a keyboard input to move the camera. Now we already use a keyboard input, so if you look at here, we've got a command glfw set input mode, and this allows us to collect the key, and we use the escape key to exit our function. Exit our program. So what we're going to do is edit the camera class. So if I go to the header file for the camera class, okay, so here we got the calculate matrices. What I'm going to do here is I'm going to just glfw window. So we're going to pass in a window object into our calculate matrices function or method, I should say. If we go to the camera class, I've got to do the same thing here, glfw, and it's going to be a window object, lowercase w in window. Okay, so this allows us to pass in our window, because what we're going to do is we're going to check for whether keys have been pressed here. So back into our CPP file. Okay, so what we're going to do is where we call our calculate matrices function, I'm going to just pass in the window object. So I'm just going to scroll back up. So in the glfw window setup, you can see we created a window object here. Okay, so and then that gets where we calculate our view and projection matrices. We're going to use that window. Okay, so that's this first thing here. Okay, what we're going to do is we're going to create three camera vectors, front, right, and up, in our camera class. Okay, so in the header file, okay, we're going to add three vectors, which are 3 element vectors. So camera front, which is a vector pointing in front of the camera, vector right, which is a vector pointing to the right of the camera, and I think you can guess what up is going to be. Okay, and we need to in the constructor, we need to instantiate them. Okay, so what we're going to put here is front. So we're going to have initially we're going to have our camera pointing down the z-axis. So our front is going to be 0, 0, and -1. Remember, we look down the z-axis, so the z-axis is actually pointing out from the screen. Oops. The right vector is going to be pointing along the x-axis, so 1, 0, 0, and up vector is going to be pointing directly up, so that's going to be 0, 1, 0. Okay. And how we're going to move the camera is we're going to use those vectors. So for example, if we add the vector front to the camera position, it has the effect of moving it forward, and if we subtract it, it has the effect of moving it back. So what we're going to do is we're going to use WSA and D keys. So W key, if we press that, it's going to add front to the camera position, and if we press S, it's going to subtract front, and similar for A and D for the right vector. So I'm just going to grab that, copy it, and in our calculate matrices method, I'm going to paste that code in. Okay, so this is why we had to have the window object being passed in, because we're going to be using it to determine whether the WSA and D keys have been pressed. Okay, we also need to update our target. Okay, so we need to update the target vector, and the target is simply is going to be the position plus the front. So where the camera is plus the front. Okay, now if I compile and run that code. Oh, we got a bug. Something failed. So and no GLFW, not GLWF. So run that again. Oh, and I got it. That same thing down here. Same problem. GLFW. Got an uppercase W. Okay, if you'd have copied and pasted those in, you should have found right. Okay. Oh yeah. So what was going wrong there? Just double checking. I think my camera was positioned too far forward for some reason. No, that's fine. Anyway, so I think our camera is actually pointing in the wrong direction. I might have made a mistake. Front. Yeah, it should have been -1. So I was actually pointing the camera in the wrong direction. There we go. So you can see we can see our cubes. Now, if I start moving around, you can see it's quite jerky, it's oversensitive. So as I'm pressing the keys, it's moving too quickly. So I need some way of slowing that down. So what we're going to do is we're going to create a speed attribute for the camera speed. Okay, so within our header file for our camera class, I'm going to create a speed attribute, and I've set it to 5. So essentially, this means it's going to move 5 units per second. If we head over to the main file, okay, well, what we need to do is we need to create some timers. And if I grab the code from here, so the speed is obviously a function of distance and time, so we need some way of measuring the time. So I'm going to copy these floats and paste them into our main.cpp. So we have 3 floats: current time, last time, and delta time. Now current time is going to be the time of the current frame, last time is going to be the time of the previous frame, and delta time is going to be the difference between the two. So we need to measure how much time has elapsed between 2 frames to give our speed. Okay, so within the render loop, just at the beginning of the render loop, so what this GLFW get time does, I think we used it when we looked at transformations, is get the time that has elapsed when the current frame is being rendered. Delta time calculates the difference between the current and previous frame, and last time we just update it to be the current time. Okay, so we need to pass that into our calculate matrices function. Okay, so we're going to pass the delta time, which is how much time has elapsed between 2 frames. We also must make those changes in our method. Okay, so it's going to be a float. Actually, it's going to be constant over the, and that's going to be delta time. Make the change again in the camera.cpp file as well. So it's going to be a constant float delta time. Okay, so what I'm going to do now is, what we're going to do is multiplying each of these by delta time times speed. Okay, and that will give us a distance. So speed was 5, and so multiply that by delta time, and that'll be some small number, because it's about 1/60th of a second would be delta time. Oh, I've made that mistake. Put that there. Okay, and this will hopefully slow down my camera movement. Yeah, you can see as I'm pressing the keys, you can see it's much less responsive, and it's sort of giving me a smoother result. Okay, so this is essentially delta time times speed. Okay, this how much the camera is going to move in one frame. Okay, so what's next? Okay, now we're going to use the mouse to point the camera, so we can move the camera using the keys. Now we're going to use the mouse. We have to make some changes to do this. So we've already captured the keyboard. So in my CPP file, we already had a code to tell OpenGL to capture the keys. Where is that? That's up here. So what I'm going to do is I'm going to paste in code, and what this does, it tells us to capture our mouse. Okay, and initially the mouse is set to the center of the window. So our window is 1024 pixels by 768, so if I halve those, and that's the initial coordinates of our mouse. Okay, so within the calculate matrices method, what we're going to do now is get the mouse cursor position. So as we move the mouse, that's going to change. So in camera.cpp, what we're going to do now is actually get the cursor position. So xpos and ypos are the x and y coordinates of where the mouse is in the window. Okay, so get cursor position stores the mouse cursor in xpos and ypos, and then what we do is we reset the mouse cursor to the center of the window. Okay. So what we're going to do is we're going to use what are called yaw and pitch angles to point the camera. So pitch is pointing the camera up and down, and yaw is pointing it to the left and right. And we're going to use xpos and ypos to calculate those. Okay, well, we need to add some attributes. So the attributes we're going to add to the camera are pitch and yaw, which are both initially pi. Okay, so in my camera, this is in the header file, camera.hpp, we're going to add our camera angles. So the reason this is pi is equivalent of 180 degrees, because we're initially pointing our camera down the z-axis. Okay. And then we're going to update the yaw and pitch angles. Okay, so what this code does, and this is within the camera.cpp, so from xpos and ypos, what we're going to do is calculate the yaw and pitch angles, which is simply the mouse cursor position minus the center of the window. Okay, and now we need to calculate the camera vectors. Okay, so there is some explanation on the lab materials here. So what we do is we update the right and front camera vectors using the yaw and pitch angle. Okay, so front, we have this 3-element vector here. I've put the derivation of this vector in the lab materials. Right is just a cross product between front and world up, and up is a cross product between right and front, and therefore we don't need that target anymore actually, because we're updating it down here. Okay, so if I run that, let's see it running. Oh, and you can see straight away I'm making very little slight changes, but it's far too sensitive. So again, we're going to have to slow down the how much the yaw and pitch angles change. So we're going to add another attribute, and this is called mouse speed, and this is going to be some small number. Now what this number is may depend upon the sensitivity settings of your individual mouse. So I'm going to set it as something very small, like 0.005. And now all I'm going to do is multiply where we update the yaw and pitch angles by that mouse speed attribute. So this should have the effect of slowing our mouse down. Okay, so there you can see it's much smoother. So I can now combine keyboard and mouse to sort of look around these boxes. Now, one thing we can actually do in these boxes is actually go inside. Right, so you can see I'm actually inside that first cube, and you'll notice we're rendering all 6 sides of the cube. Now, if I go outside of the cube, that's sort of wasted effort, because at any one time I can only see 3 sides of any of my cubes, and that's wasted effort. So we could improve, or we can sort of make things a bit more efficient by using backface colouring. Before I do so, I have forgotten one problem with our current application. So if I go down, if I try and look down on my cubes, so I'm above my cubes now, and I look down, you'll notice in a minute, yeah, it's suddenly switched. Okay, I've suddenly flicked a direction. The reason being is when we point the camera straight down, it suddenly flips. So what we can do is we can constrain the pitch angle so it doesn't go, so I can't point it absolute straight down. Okay, so to do that is after you've updated your pitch angles, we have a little bit of code here just to check and to limit it. So if I run that now, and again if I go above my cubes, you can see I'm trying to look down, but it's not letting me. So that's one way around that problem. Okay, so I mentioned before we're actually rendering all 6 sides of the cube, which is wasted effort really, because we can only see 3 at one time. So we're going to add something to our code which is called backface culling. This is very easy to do. Okay, so there's a command here which we can tell OpenGL to essentially only render those sides of the cube which are facing the camera. Okay, so where we enable the depth test, I'm going to enable the backface culling. Okay, so if I run that code, okay, again I'm going to go inside one of my cubes, and you can see I'm not rendering the sides of the cube which are facing away. So if I just go inside again, you can see. So whereas when we're outside the cubes, it looks like we have 10 solid cubes here, what we actually have is we have half as many faces being rendered. So we're only rendering those which are facing the camera, and that's called backface culling.